Perfect. Yeah, then hello everybody. I'm Sebastian. I'm a fourth year PhD student here in Germany, together with Ulm University and also Bosch Center of AI. And in this talk, I would like to present to you RelationField, relate anything in Radiance field. This is actually a paper that we got accepted at CVPR 2025. So this will also appear this year at CVPR. And this is not just my work. I'm the first author, but there's great contributions by all of my co-authors from Ulm University, Bosch, Google, Technical University of Vienna, and TUM. Yeah, so today I really want to talk about radiance fields. In recent years, radiance field approaches such as NeRF or Gaussian splatting have been on the rise, and combined with 2D foundation models such as Dino, Clip, SAM, or Stable Diffusion, they form so-called feature fields. And these feature fields can be used for tasks such as open vocabulary localization or interactive instant segmentation. While NeRF originally was proposed for novel view synthesis, it is really ideal to lift these 2D foundation model knowledge to 3D, as NeRF directly models the underlying 3D geometry, but it is exclusively supervised by 2D images, which can be used, these 2D images then can be used to extract 2D foundation model knowledge, which we can then have in 3D via the NeRF. However, existing approaches mainly focus on object-centric representation and completely ignore object relationships and their interactions. And in this talk, I would like to argue that relationships are very important for 3D scene understanding. Maybe we can look at a very simplified example of a 3D scene where we as a human would ask a robot assistant to maybe fetch the chair close to the cabinet here. Notice that there are actually two chairs in the scene. One is close to the table, which is probably needed by a friend or colleague, and one is near the cabinet here, and is probably available to use. We of course want the free chair, and therefore it is important that our robot assistant kind of can differentiate between these two. Historically, 3D scene graph methods have been proposed to kind of solve this problem of encoding not only objects, but also their relationships in a graph structure, such that we can reason about object relationships. However, these methods often require reconstructed point clouds. They're expensive to train, and they do not offer this kind of interactive querying seen in these feature fields that I've shown on the slide before. Therefore, the goal of this paper that we are proposing here is to propose a feature field that encodes not only objects, but also their relationships, similar to what we've seen from 3D scene graphs, but a method that is only learned from 2D images and is similarly interactive as methods such as these feature field approaches such as LERF. So let's look a little bit more into detail into how NeRF is built. NeRF is a neural network that takes as input a XYZ position, as well as a viewing direction of the camera, to predict a density and RGB feature vector for the given input. And so now when we execute this network for the entire scene that we have and render its output to a 2D image plane, we essentially get the novel view synthesis setting that we all know from NeRF. And now what follow-up work such as LERF did, they extended this NeRF formulation by proposing an additional output feature that is supervised by a foundation model, such as, for example, Clip. And you can see here how in LERF we can query different textual labels that are encoded with Clip to, for example, localize here the soap So here you can see the activation label that was generated by LERF, and this is of course now in the 2D rendered image, but this actually exists in the 3D representation itself. And here we can also see like more higher level concepts such as yellow, which also gets recognized by the LERF model pretty much perfectly. But so what we now want to do in RelationField is we want to extend this NeRF formulation even further by proposing an additional language output for the relationship feature that is similar to LERF, except that now it's for relationships. But furthermore, and in contrast to LERF, we also modify the input representation of the NeRF model by having or introducing a secondary XYZ input query. And so this secondary input query basically acts as a condition for this relationship feature. We do this because we kind of identified that while objects kind of exist on their own, for relationships, you kind of always need a reference point to actually relate something with something else. And so, for instance, here we have these bottles here. These will act as our anchor point or reference. And then in the Radiance field, we want to predict the relationship feature for these bottles. And so, for instance, you can see this here. So here we queried, when we selected the bottles, we query standing on, and actually our model successfully identifies here that the bottles are standing on the shelf. But this, of course, works not only for a singular object in the scene, this works for essentially all objects in the scene, and also the relationships that we encode are truly open vocabulary. So we can model, for instance, relationships that describe composition or that compare stuff, spatial proximity, or even affordances, and this support relationship here. So how do we train this network? Essentially, we generally follow the normal NeRF practice. We shoot an array into 3D space from our camera, but now with our additional secondary XYZ query. And then, so the output of the network will be the normal RGB and density known from NeRF, the object feature that can be very similar to LERF, and then our new relationship feature. And then we essentially take all of these outputs and use volume rendering to render them onto the 2D image plane, such that we can have a training loss entirely on 2D image supervision. For the supervision, we roughly need 50 to 200 images. This mainly depends on the size of the scene or the complexity. And then we actually encode all these images with a foundation model. Here we use ChatGPT because I guess ChatGPT at the moment is the most powerful foundation model. And we actually use something a little bit more fancy, which you might recognize from the previous talk. We're using set-of-mark prompting. So we kind of we auto-generate masks for a given image, overlain with these tags. And then using these tags, ChatGPT has a much easier job captioning this image for the relationships that we are interested in. And so we kind of prompt the ChatGPT model in the sense that it outputs us nice relationship descriptions with an identifier for each object, and then the relationship label that ChatGPT extracts. But of course, we cannot directly use these captions for training the NeRF. We actually need higher dimensional features that we can then encode in our NeRF. And we do this by essentially encoding these ChatGPT captions with a language encoder such as BERT, and then place the encoded language embeddings of the relationship back into the image space based on the identified tag labels that are consistent between the captions and the image space. So what we will end up is that one image will essentially spawn multiple relationship feature maps. Each feature map encoding a relationship between two objects. And essentially we do this for all object pairs. And then to train the NeRF model, we utilize a pair pixel sampler, which samples pairs of pixels on these 2D feature maps for supervising the ray coming from the NeRF model. And so essentially the training is done using a simple cosine similarity loss that we use for distilling features, such as the features coming from the NeRF model are similar as to the features that are coming from the 2D supervision. Here you can see a quick demo of how RelationField works. Here, for example, we select this bottle and then say standing on, and we correctly get the shelf. Then what we can also do is here we select the soap because we want to clean the dishes in here, and we say cleaning with and get the sink for cleaning the dishes together with the soap. Here, another selection of like this coffee grinder we are standing on. So these relationships are really object specific. Here we query the knife and ask hanging on. You can also slightly see that it actually favors more the knife rack than the wall. Here we select actually the freezer part of this freezer refrigerator combi. And when we ask part of, it gives us the rest of the refrigerator. Here we select the scissors and ask hanging on. And what you can see is that it really highlights the wall and not the objects that are also hanging on the wall. And yeah. And this, of course, works not only for one scene. This works for any kind of scene that you want. So it can be kitchen, can be bedroom, can be bathroom, can be living room. With all kinds of relationship queries for different kind of objects. It's truly open vocabulary. And one thing that I would love to highlight here are these functional relationships. So what we queried here, I think it's a little bit hard to see, but essentially here we selected the light switch and queried our model with turns on, and actually RelationField outputs correctly or highlights correctly the light in the room. Which actually can be quite useful for a robotic agent that is tasked to turn on the light. It kind of has to first know that to turn on the light, the agent doesn't have to interact with the light directly, but it has to interact with the light switch. So this can be also very useful for any robotic downstream application. By then combining our relationship semantics together with the previously existing object semantics, we can also get like a complete holistic 3D scene representation as a 3D scene graph to also compare with more classical methods to solve these referral problems. So how do we do this? We run our RelationField approach slightly different to how we would use it to render these activation maps. First, essentially, we don't care about the camera viewing direction and the RGB output because now we want to really reason about the underlying 3D where we don't need this information. Then in kind of an initial step, we utilize the density the density of our NeRF output for a scene to essentially get a 3D reconstruction of the scene, where essentially here we have a point cloud where each point essentially represents one XYZ location that has positive density, so where there's actually an object. Then we can use this object level semantics to do like an initial 3D instance segmentation to get all the instances, which will form essentially the nodes in our scene graph. And then in a fully automatic process, we can essentially treat each object instance as a node in the scene graph, yes, but also a relationship query for our RelationField. So here, for example, we select the pillows here So this will be one node in our edge that we want to construct for the scene graph. And then we can, for example, query the relationship lying on. And then for the entire 3D reconstruction, we will get an activation map, which obviously will be higher for the sofa region and lower everywhere else. And then in the final step, to get the full 3D scene graph edge, we can again use the underlying instances, which we extracted from our object field, to essentially aggregate these activations onto individual instances. And here we then see that the pillow that we originally selected has the most activation with the sofa instance here. So this will be our other node in this relationship edge. And like this, we kind of constructed one edge in the scene graph, and this we can, of course, repeat for all nodes or all instances in the scene with also different relationship queries. And this runs in a fully automatic manner to extract essentially the full 3D scene graph. And what is nice is that using this process, we actually achieve state-of-the-art 3D scene graph prediction performance when you compare against other open vocabulary 3D scene graph prediction methods. So we essentially propose this relation field based on the NeRF backbone, which works quite nice, right? But the community has now largely also moved on to Gaussian splatting. So the question is, can we also apply our relation field to Gaussian splatting? And the answer is definitely we can do this. However, compared to the NeRF variant, there are some tricks that we have to do to kind of fit this training run into GPU memory. So while in the NeRF setting, we essentially optimize geometry and the feature field jointly. So we learn the density in RGB at the same time as the relation field and object features. Here in the Gaussian splatting setting, we first train a Gaussian splatting field with all the Gaussians that reconstruct the scene. And then in the second step, we use our small network hat for the relation field, which then has these two XYZ queries, which will be the centroids of each Gaussian to learn the relationship feature and the object feature. Using this, we achieve a roughly 4 times speed up with Gaussian splatting. So here we can relation field with Gaussian splatting. We can run at roughly 7 frames per second, which is maybe not real time itself, but it's actually close to real time when you compare like the pre-processing that we've done with ChatGPT. This was obviously much slower. And with this approach, we kind of can do near real-time relationship reasoning in a 3D consistent manner. However, when we make the switch from NeRF to Gaussian splatting, we definitely also see an increase in GPU memory. So depending on what your hardware requirements are, there's a trade-off between the NeRF and 3D Gaussian splatting variant. The quality that we get out of a relation field with NeRF and Gaussian splatting is similar, I would say. Maybe the NeRF reconstruction is slightly higher quality. The reason that this is mainly because we have this joint geometry and semantic optimization in the NeRF, which is kind of missing from the Gaussian splatting reconstruction. Additionally, in this paper, we propose a new complex open vocabulary instance segmentation benchmark to essentially evaluate a relation field against the previous state-of-the-art that focus more on object-centric representation. We propose this benchmark to really focus on the complex relationship oriented queries. So what we did is we labeled essentially 8 scannet++ scenes with over 30 unique relationship queries, more if you consider duplicates. And the focus of this benchmark is really to have queries that focus on the relationships to test essentially whether the network that we test attends to just the objects that are in the query or actually understands the complex textual query. To kind of do this, we select mostly scenes and queries where more than where two objects of the same type are present, but only one of them is actually consistent with the relationship description. With this new benchmark, we evaluate this against the current state of the art for open vocabulary object localization. And we see that RelationField produces the state of the art for this task of open vocabulary localization of objects based on a relationship query. We measure this via the intersection over union and accuracy. And especially when we look at side-by-side comparisons. For example, here we have a scene of a monitor that is standing on the desk. So this is actually the query. And for example, OpenNeRF, which is a competitive baseline, it produces high activation for the monitor, yes, but also for the table here. So it kind of confuses the object of interest, which is the monitor, with the additional description, which is the table here. In contrast, RelationField, which can reason not only about the object itself, but also the relationship, is able to correctly predict that we care about the monitor here. I think it gets even more clear when we look at this example here, where we are querying for a curtain that is hanging on the door. And OpenNeRF actually confuses this query very drastically. For example, here we have another curtain that is covering the windows. And here we have like a closet door. And so essentially what OpenNeRF attends to is just the nouns in the query. So it has curtain, it has door, it has curtain here. Meanwhile, even though our RelationField prediction is a little bit more noisy, our network is able to correctly identify that we are interested in the curtain hanging on the door. And with this, I already come to my main takeaways. RelationField enables this novel 3D relationship reasoning, which is entirely enabled from 2D observations. We essentially redefine what relationships are in 3D as a pair of rays in this NeRF formulation, and we can capture spatial and semantic interactions between objects. Also, RelationField encodes powerful foundation model knowledge. Here we use ChatGPT and makes these relationships queryable in near real-time performance, which is definitely not true for the base foundation model. And of course, RelationField can model complex and causal relationships, such as the light switch with the light, which can enable a diverse set of downstream applications, especially in the robotics domain. And with this, I would like to conclude my talk. And if you have any further questions, feel free to ask.
Fantastic. So we are running a little bit behind, but I do want to get to two quick questions. The first question came during your 3D scene graph prediction slide. And the question was, can the otherwise identical relationship between two objects be dependent on what room they are in?
So in this scene graph construction setting, we consider only single room scenes, but is also applicable to multi-room. The challenge appears, of course, if you have multi-rooms with like objects that have a similar relationship connection. But in theory, because we do a first instance segmentation over the 3D scene, we can extract every unique relationship between objects.
And let's do a quick 2-for-1 question. And these two questions came during your NeRF versus Gaussian splats side. First question was, how computationally intensive is your process? In other words, how long does it take to run per Gaussian splat and on what hardware? And the follow-up is, how sensitive is your system to Gaussian splat artifacts?
So we run this, or we test this on a V100, where at inference time, the Gaussian splatting we can run at 7 frames per second with 27 gigabytes of memory used. The training time, because we have to do training essentially for each scene, takes roughly between 1 hour and 1.5 hours. But then it's near real-time performance.